Okay, so welcome. As you can see, this is the One API to Rule Them All talk. Alois and I will be giving this talk, and we both work for Time Out London. It's a bit of a funny title. Alois deserves the responsibility for that one. Either good or bad, depending on how you feel about it. So in this talk, we'll have the rough structure. I'll start by giving the motivation and why we've done this work. After that, Alois will talk about Shona, which is this library we created for the work that we'll be discussing. He will describe the graph DSLs, the entity library, and the execution engine. Shona is quite a bleeding edge library. It uses macro paradise, so it's not just macros, but it's the macro paradise branch. And Alois can tell you some funny stories about what happens when you use snapshots instead of actual real build. And then after that, since it's quite a bleeding edge library, there's quite a bit of work we still want to do and we need to experiment with. So we'll describe a little bit what that work will be. And finally, at the end, there'll be some time for questions. So why did we do this, and how did we get to this, to experiment with this particular approach? So the use case is quite simple, and it's one that I think many companies have. We needed to create an API, and we wanted the API to be flexible, to be used by different devices with different needs, while still being, a single API. So we looked at what was out there, and we saw the Facebook Graph API. Seems to make sense. It allows you to select fields based on the field expansion feature, and we said, okay, why don't we do something like this using Scala, which is what we use for at Timeout. So we once we started thinking, okay, so we describe our domain as a graph. Then it became apparent that actually we could use this for a lot of other things. We could use it for feed ingestion, for migration of data from new cities, as well as redirections and a bunch of other things. So the basic approach was always the same. Create a graph to represent each domain and have a few transformations between each domain. So of course, this particular situation is not just a timeout situation. Many companies these days need to have an API that targets multiple devices. Companies want to reach as many users as possible, and they want to reach users in as many contexts as possible. And when you cater the fact that mobile applications, mobile devices often have more restricted bandwidth, then it's important to provide a flexible API and an API where you can constrain what you return and that you can optimize for each device and use case. It's also important that you support innovation. So certain use cases may require different data from the backend, and you don't want to be the bottleneck. You want to allow the client team to innovate and use and change the API as they need it. So I'll talk a little bit about how the progression we've had at Timeout, where we started with a single API. It was, try to cater for all the use cases with this single API. And in the beginning, it was working okay. But then as the use cases started becoming more complex, the web team wants certain fields, the mobile team wants different fields, the mobile team wants to make less requests, you have to cater for all of these things, while still maintaining the conceptual integrity of the API. So, you start introducing ad hoc ways to customize the response. Have a request parameter here to, for example, perhaps return fields that are bigger and so on. And this is a road to a very big mess where, there's inconsistencies and it's difficult to understand and to maintain the code. So eventually, you even start introducing device-specific endpoints, and finally, you end up with multiple specialized APIs, which are hard to maintain because whenever you add a new feature, you have to add to all of these APIs instead of a single one. So then, as I said before, we wanted to have this unified API that was also flexible, similar to how the Facebook API works. And the idea is that you have these graph queries that can be joined. And once you join them, you can return them in a single call, but you maintain the data hierarchy. So by maintaining the data hierarchy, it means that instead of having custom parsing code for each type of, like batch operation and stuff like that, you can have the same parsing code, but then, while not having the problem with multiple calls and having the efficiency that you need. As you can see in these two APIs here, in these two examples here, it's quite flexible, the API. It allows you to limit nested fields, to select nested fields, and to also do filtering. So for example, in the second example, only videos of type tagged are returned. So this library Shona that I mentioned, allows to do something like this in Scala, and using some of Scala's functionality to do this in a type-safe way. So Alois will explain that in more detail.
Hi everyone. So I'll present you the basic implementation of what we have today, which is far from complete, but which is our first step in experimenting with that approach. So first I just want to explain the basic components of the system. So we have a graph model language, which enable us, basically it's a Scala DSL, which enable us to describe that domain graph. Then we have a graph query language, which is currently based on JSON query. I will explain later in detail how that is working. And once we apply that query on the graph, we need to output something. So we created a little entities framework, and I will as well show that. So basically the execution engine is applying a query on the model and gives the result out. So here is more concretely what could be done. So for example, we have a model which is film, director, and review, and we have a relationship between film and director and film and review. So if we apply that query on the graph, we expect to get this kind of data as a result. So here I just saw some JSON data, but what we really want is a Scala data structure that we can use in Scala code, and not only when it's accessed through a JSON API or something like this. So now I just do a little parenthesis about the technique we had to use to do that. Because the challenge here, as I said, is to have a data structure which is dynamic, but which support a set of fields where we keep actually the type of each field. So we keep all the safety once we use it in our Scala code. So, and as well, we want to be able to access it like if it's a class or a case class, let's say. So to do so, we need to encode the label of the field in the type. And currently, there is nothing in Scala which allows you to do that. Ideally, what would be nice is being able to do this. So code through that type. So this is something which is not supported currently, but which exists, in fact, in the AST and in the compiler. So something that Miles Sabin did actually in Shapeless, not in the release of Shapeless, but one of the experimental version which used macro paradise. He created a type macro which actually exposed this. So here we see, actually this is a type. You call label and you give a string. And this will generate a type which is actually a subtype of string, but which contains the actual value of the string. So this is a technique you will see later that we'll use to encode this kind of information in the type. And I understand it might be a bit confusing now, but it will make more sense once I show the other example. So let's start first by the graph model language. So it's, as I said, it's an internal DSL. It means we do everything in Scala there. It can be traversed at runtime because the graph is values, right? So you can create function which traverse it. So the first implementation I did when we first had this idea with Ismael was like a proof of concept in something in 2 days. So I was able to get something working really quickly, only with runtime stuff, and by integrating with Slick. So at that point we said, okay, so it looks like the concept is feasible. And later I restarted the project from scratch, and I said, will it be possible to do it, but with having all the compile time safety, as much as compile time safety as possible. So here the challenge was being able to encode all the graph in the type, and then to traverse that graph. So currently, the way it's done is by using a def macro, and we have some utilities which extract the the vertex, the edges, and the thing from the type, and enable us to traverse this. It should be possible to do the same with implicit resolution. The same way it's done in shapeless when you actually map H-list or something like this. But I think the performance will be horrible. So I think it's something to explore because it might be interesting in terms of experimentation to see if it's actually feasible. But at the moment, we didn't look into this because it wouldn't be really useful for production usage or things like that. So now let's look first how the DSL to define the graph looks like. So basically here we are defining 3 vertices. And so first thing, we give the vertex a name. So here there is a kind of special syntax because in Scala you can't partially apply a type. If you want to give a type explicitly to a method, you need to give all of them. You can't just give one of them. So one of the tricks here is that here you're calling the vertex.apply method by giving a type parameter, which is actually the singleton type of the string. And in fact, this returns a vertex builder, which have a method which is tilde, which then receive a list of properties and create really the vertex. So by doing so, we can infer that type and give that one explicitly. So here then we define all the properties of that vertex. We give it a type, and we give it the name for each of the properties. And we repeat the same for the other vertices. So then let's put these vertices together to create a graph. So it's the same graph I showed at the beginning. So we have a graph companion object which takes as first parameter group the list of vertices. And then the second parameter is a list of edges. So here you see the edges directly inlined into the constructor, but of course you could define it in a val or somewhere else. If you start having a big mapping, it might be better to put that somewhere else. So here we define an edge, we give it a name, so the same name as we see here, and we say from and to for the connection, and then we define a mapping. I won't go too much into details here, but basically it's what enables the execution engine to know how to link data together. So you can think about a foreign key, and ideally once we do a proper slick integration, this kind of information could be generated directly from the table and from the slick schema, basically. So then let's see, this is a DSL that you will use once you want to describe your graph. And I think what is interesting to see is how this information is kept into the type behind the scenes. So let's look at how the class and the type are defined. And here you will see some pattern which repeat between the different type, between the different class, and which is something you could use for other projects and other needs. So first, we have a vertex which have a list of properties. So what a property is, it simply have a name, which is here in form of type and value. So this is actually part of the trick used with the shapeless type macro. So without going into too much detail, it gives you the possibility to have the name encoded here, the subtype of string, and as well as a value here. So it means at runtime you can get it. The second type parameter is the type of the property. So for example, if it's ID, it could be int, long, something like this. Then we define, here is the class, the basic type for the vertex. So same thing, there is a name for the vertex. And then there is a list of properties. So here we are using H-list. So for those who are not familiar with this data structure, it's basically, for example, if you create a list, and inside the list you put one string, one integer, one long, the inference will give you a list of any. And it's not really useful because you lose the type information of all elements. So you could use a tuple, but a tuple have a fixed size. So if you want to have both things, you need to use a H-list, which basically constricts your list of elements, but keeps the type information for each of them. And here it's very important to keep the type information because we have the name as well as the type of the property. So here we define properties as a subtype of H-list. And here this kind of crazy syntax comes from shapeless and is actually a type class which witnesses that all the entity of the H-list are a subtype of this one, which basically any property is just a type alias for property string any. So it's It's to be sure that once the end user creates a vertex, all the elements of that H list will be of type property. So this is a pattern you will see in the other class, which is, I think, quite useful. So this one is a bit scary, actually. You shouldn't be afraid about all the type parameters. So basically here we define an edge which have a name, a vertex which is from, vertex to, and then the mapping. So the mapping actually define which property we want to map from and to. So if I go back to here we defined that director ID point to the ID, or here the ID of the review point film ID. So this is what we define actually here, and we infer the type, the name of the property as well as the type of the property. So then when we compile, we can be sure that the edge we are defining currently use property and vertex which exist in the graph. So finally, the last one is the graph itself, which take a list of vertices and a list of edge. So here we use the same technique as before. Both of them are H-list type, and we add the type class to be sure that all the type are of what we want, which is any vertex or any edge. So this was for the graph model part. Now let's look at the graph query language. So we choose to use JSON query as a query language because it's very simple. So for those who don't know JSON query, it's similar. Most of you used XPath or XQuery. So this is the equivalent of XQuery, but for JSON. Why preferring that versus XQuery? I think it's probably the same reason to prefer JSON versus XML. I mean, the syntax is easier to work with, and yeah, I think just simple and yeah. So currently, the implementation is not the full implementation of the JSON query specification. We only support a basic map operation. I will show some example just after. It's what we've seen at the beginning. So we want to be able to use this query as in Scala code as well. So what we did is that we created a macro, which actually you can give the JSON query string, and it will be compiled and added directly during the compilation, versus using it at runtime from, for example, when you have an endpoint which receive this kind of thing. So the current implementation is done using Scala parser combinators, which is a quick way to implement a parser, and yeah, it's really nice to be able to combine the things together. One of the issues is the performance. So we didn't benchmark or things like that, but I think it's a pretty known fact that parser combinators are not very performant. So this is something we should probably improve later. So let's see some example actually of how this graph query language could be used on an object graph, which is the reason it was created at first. So here we have a simple JSON object with a film which have a name, a director with an ID, and a name as well. So this is a JSON query. So it's simply defining the path of the data we want to retrieve. So we say film.name, and we get empire of the sun. If we say film.director.id, we just get 1. So then here it's a slightly more advanced query. This is we can think of it about like if it's a map in Scala, and so we say we want film, but we don't want all the field, and we map on it to get only the field we want. This is especially useful if you think about someone which want to create a custom API or creating a feed from the data from your domain, because you can say, okay, I just want this information, and get a flat view, which is often needed. So now that we had the graph model's JSON query, once you apply that JSON query to your graph, you need to output to get the data out. But you don't know before what will be the format, and you don't want to create one case class for every possible input. So it's where we created that entity library, which I think is quite useful and is quite self-contained as well. So this is something which could be used outside of Shona actually, and maybe some of the feature will land directly into Shapeless, probably to improve the record support. So basically an entity is a H list of field. So before we seen property, it was just defining the type and the name of a property. A field is the same, but there is a value. So, for example, ID equal 100. So an entity is simply a H-list of fields. So we use the same type class here to witness that the type will be correct. And so the good thing with that is that you get for free all the utilities from Shapeless. So you can map over it, you can take, you can drop, you can do everything you want. You can as well manipulate it dynamically at runtime. For example, if you want to provide a very flexible API explorer like Facebook is doing or things like that. So to do so, you could convert the H list simply to a list, and then you could do runtime things. So let's see how we can use actually this entity library. So the first thing is that we have as well a DSL for using the entities. This is not directly used by Shona, because usually when you apply a query to your domain graph, the entities are created by the execution engine, so you are not doing it by yourself, but this is to show that it can be used really as totally independent library. So here we are creating an entity with two fields. One of the field event name ID with value 1000, and another email with another value. So the thing is that this is very flexible because you have it's based on an H list. You can do a lot of interesting operation in it, but if you want to use it as a traditional case class, the syntax is not so good because you can need to do, for example, .head, .tail, .tail.head to access a field. You could access some field using a natural number, but it's not really straightforward. So something I experimented with is creating a kind of view system. So currently it's implemented using introduced level of macro paradise, which will very likely never happen to land into the trunk of the Scala compiler. So we need to investigate how to use annotation macro actually to replace that implementation. But the interesting thing here is that you ask for a view for that entity. Behind the scene, a macro will generate a class which will wrap that entity and create each field that you need to access it. So it's here that we realize how it's handy to have that label information encoded into the type. Because as you have this information at compile time, you can actually create some utility which expose this label. So here we see that we create that view, and we can then just access the field and see that the value are here. And another nice side effect of this is that you don't have any 22 limit or any other limitation that you have with case class. No, it's because actually the code comes from a specs to test. But which in fact is a bit the same of Scalaz because the type is checked as well. So now that we see the main building block of that system, I'll show you a run of the execution engine. So currently the implementation is very simple. It's mostly for demonstration purposes. So it supports only one-to-one relationships. So you can do optional relationship or one-to-many. It's read-only. There is no parameter support. So it means that a mapping is just only describe how to get one node from another. But you can do, for example, pagination or asking for doing filtering to ask an entity by ID or thing like that. So and as well, entities are loaded using in-memory data structure. So it's just to show how the different pieces fit together, but it's really not something you will use for production or thing like that. So actually, I wanted to do a live demo. And so I have the syndrome of it works on mine because it works on my laptop, but probably because an nightly build of Macro Paradise was published that night, and on that computer it doesn't work. So I will have to do a demo with slides, unfortunately. So here we have the model I described before, so basically film director review with the graph defining the different edges. So one interesting property interesting feature we got by using Shapeless is that if, for example, you remove this, the compilation will fail. Because by using the type class, you are able to know that you create an edge which references a node which doesn't exist in the graph. So you have a full safety at the level here. I won't show you the compilation error because it's kind of crazy implicit resolution message. It should be probably improved by adding some implicit not found annotation in the code, but it's nice to have, but not critical for now. In the same way, if you define a mapping which points to a property which doesn't exist in the graph, this code won't compile as well. So here we see how handy as well it can be to have directly the label encoded into the type. So now I just briefly show you some type class which I created to work with the execution engine. So for the execution engine to find the data actually. So there is two type class, which is entity loader, entity finder. And here I have just in-memory representation of the entity. Ideally, this kind of thing should be replaced by a nice integration layer with Slick or with web services, for example, because in some case, some data are in your internal system, but you have some references to an external systems. So we could easily create some type class and combine them together to get the data needed. So here is a REPL session. I hope it's big enough to see something. I don't know if I can. Yeah, I don't think I can do something better. I'm sorry for that. So actually, we just import the different package needed to work with this. Here we import the model files that I showed before, and the provider file, which include all the entity loader and entity finder. So then we have a macro actually, which is execute, which calls the execution engine. We give it the graph, and we ask, and here we give the JSON query. So here we just ask for films. So actually here we have a very interesting type, but at the end we see that we have a list of entity with the name of the movie and the other field, like the director ID and the other information. So then we can do a more complicated JSON query where we actually define a mapping. So this is a query we seen before when we ask for film, but we ask precisely for the film name and the review rating. So in the same way, we get back the entity with the name, the rating for each of them. So then these entities as is can be useful to, for example, expose directly to the REST services or things like that. But if we want to use them directly in Scala code, the best thing to do is to create a view. So here we see that kind of not exactly dynamically generated, but we have a new type, new class which was generated, and which is in fact the view which encapsulates and wrap the entity inside. So then you can simply do call .name or .rating, and you get directly the value with the correct type, string and int. So it means that then if you create another DSL which describes mapping from the graph, that graph to another graph or another system, you can ensure that the constraints of the type are correct and that it won't fail once you run it. So the idea that you could create some very simple DSL that can be used by someone which have no clue actually of what's going on behind the scene. And yeah, so I think Ismael will show that after some example of how this could be used concretely. So, but to do so, we definitely need a string singleton type. So we don't need a type macro, which we won't have anyway, but we really need to be able to do that. So yeah, we had some discussion with some type-safe compiler hacker. So it's something they want to provide at some point. But yeah, so we don't know when we will be able to start really integrating this and using for production system, as long as we don't have this feature into Scala. So then I will give the hand to Ismael to show some concrete usage of what you can do with this graph.
So, like what we've shown right now is really a prototype, and there's a few things that we need to sort out before we can use it. But the first real use case that we intend to use that timeout is to use this to help us with the feed ingestion problem. Timeout is planning to expand over 50 cities, and each of these cities will have a data feed, many data feeds, probably around 5 to 10. So it's a lot of data feeds, and it's not feasible to implement each of them manually. So we're trying to, create an automated system where it requires very little development involvement to map a new feed. where most of it can be automated as well, not just the mapping, but the testing of it and everything. So on a very simple, the very simple idea is that you define a graph to represent the feed that's incoming, and then some mappings from that to the domain feed, let's say, and then the framework would handle the translation. The demo that Alois gave earlier already does something similar to this, but of course the devil is in the details, so a lot of work will be required to actually get it working for all the edge cases. Another scenario where we want to use it is for redirects. At the moment we use something like a combination of Nginx rules and a routing table, and it's a very ad hoc mechanism to do redirects. As if you do web applications, websites, that URLs, you have to create redirects for search engine optimization reasons. So, we're thinking that using an approach like described there, where we map a particular path to the actual entity in a more principled way, will allow us to simplify a lot of the messy code we have in this area, because it's a source of many bugs. As Alois said, the current implementation is currently only using an in-memory computation. It's not actually going to the database. We had an implementation that was going to the database, so we need to re-implement that using the latest refactoring to make sure that we actually have something that does something useful. But another thing that we think is very interesting is integrating this with Spray, which is what we use for our RESTful API. So if we could generate the Spray routing and as well as the documentation for it automatically from the graph, it could save us a lot of work. It probably wouldn't replace the whole thing, but it would get the basics in place. And
so some next steps as well is that it would be very interesting to try to port all the thing down in the entity library directly into Shapeless. One of the main advantages of doing so is that by using the Shapeless record system, we could get serialization for free. And it's so maybe some of us seen the Pickler Spore talk today. So basically, what you can do with Shapeless is kind of similar to the Pickler, that you have reflection-free serialization. So basically, the hlist of fields, which is the entity, could be serialized without reflection, which is quite cool, I think. Another area where we really need to look into and improve the stuff is a mapping support. So currently, as I said, it's just a one-to-one relationship, very simple. So we want to be able to define mapping kind of functions so they can receive parameters, which will then be used by the execution engine or by other things, which is kind of the equivalent of querying parameters in the context of a REST API. This will give us the capability to do pagination support, and as well to support create, update, and delete, as today it's only read-only API. So that's it. If you want, you can find the source code on GitHub. There is multiple branch. The master branch is really everything which is stable, which doesn't include the execution engine.
Stable.
Yeah. The master one is stable. No, the master one is stable. But there is some topic branch, one with only the execution engine, and another one which the context of the demo here. So that one I probably have to look into what's happened with the last nightly. So and as well we are hiring. So if that looks cool to you, don't hesitate to contact us. That's it. Thank you, guys. Yes.
The question is, do you have some different kind of models for presentation and for internal processing? As you know, you might not have want to expose some field.
Yeah, very good question. So the idea is that what we want to do, we are using mostly Slick, right? And there is some new things which will arrive to Slick, which are the distributed scheduling. So it means we'll be able to use different systems, like for example NoSQL and SQL. But then you don't want to expose all your fields probably, or maybe you want even to merge some table together. So the idea is to be able to define a kind of mapping from the Slick schema, for example, to that graph. So yeah, so you won't expose directly. Well, you could.
I mean, the is just for exposing.
Exactly, it's only the representation. Yeah. No, so it's interesting actually because it should be possible to reuse this internally in Scala, like eating your own dog food. So we could potentially create a Scala driver which uses that graph. But I don't really think it will be useful because it's more for really creating, exposing that outside, and not. I don't think it's something to explore and see if it will make sense. But I don't think it will be useful.
And the second question is, what approach to pagination do you see? Because usually there are two approaches whether the sequential requests are consistent around these pages and the content of the pages or not. And when you want to maintain this consistency, you should store some state, and that might be...
So we definitely don't want to store any state. Then I think it depends of which database system you use. For example, if you use Cassandra, you could rely on the UUID to do the pagination and like giving a next one and stuff like that. If you are using a SQL database, you will probably use the offset approach, I think.
Yeah, but the content could be changing.
Yeah, if you use the offset approach, the content could be changing, yeah.
For our API, I've made it really fast. Just, I'm defining whether the response is curable and making some kind of take or sublist to then respond with it. So
I see.
The responses are not consistent in time.
Yeah,
you don't need to store this state.
Yeah, I really prefer that.
For some clients, it might be useful.
Yeah, I think I really prefer that approach than something else because.
That was made in 30 minutes.
Yeah. I don't think it's a big deal actually to introduce that.
I mean, you could come up with some more complex measures if you felt like that was required. But I think that's probably something further down the line because there's so many basics that's still missing.
Yeah. But I think it will be one of the interesting challenges to support that correctly.
Generally, client developers are expecting that you are actually providing the state.
Yeah. No, we really don't. I mean, it's to expose a RESTful API, right? So you don't want state. You can have state, but as a, how do we say, as a hypermedia stuff. So you could keep state into the query parameters, but you won't keep state in session on the server side. So yeah, but you can see the REST API as a graph. If you really do RESTful things, when you only start with only one URL and you follow that, you have no state, and it really.
You might think of it like you might tell that the client that you have n size of pages, and to give the ability to use any of the pages with the amount of pages could extend.
Yeah.
Yeah, in general, you want to expose only the next page, right? Because that gives you more flexibility. In the previous, the next and the previous, not all of them, so that gives you more flexibility in terms of efficient implementation.
That could be, during the time the new pages can occur.
Sure.
Yeah, I think it's something you can live with it. But it depends really of the use case. For us, it's really, it's because probably we have a very simple domain, right? That we can model it as a graph like this without state and things like that. So it won't work for everyone, I think, yes?
Did you look at another graph backing, like a graph database to actually run it out of?
Not yet, but I think it's an interesting thing to explore. I mean, we didn't want to change the back end of our current implementation, which is MySQL for the content stuff, but I think it would be something interesting to explore.
I think especially what you guys shown today, the data.misc implementation, which, as you said, you could model as a graph, right? Yeah. So I think it's something which integration with a system like this could be really interesting, I think.
I have a related question. If you look at graph query language, like Gremlin or something.
Yeah.
Because it would be interesting to.
Yeah, definitely. So I think if you want to go more in a kind of semantic approach to the thing, it's definitely something you should look into. Sparkle as well, or things like that. But for now, it's we have really simple needs. We don't want to do complex processing like that. But it's something which will be very interesting to explore, indeed.
Especially because it's one of them emerges as de facto standard.
Yeah.
So it would be nice to take, let's say, Gremlin query. And,
And then it's more than just a REST API, but it become a kind of web. It could become kind of web semantic framework or something like that here. Any more questions? Thank you.
Thank you.
All this microparadises.
Yeah.
It hasn't changed for
So maybe it's not because of the nightly. I don't know actually.
So have you previously built?
How are you doing?
No, not on this machine. So maybe is there something with